introduction. All right, so for our IQS seminar this week, we're happy to have the inaugural fall semester 2024 seminar given by Robert Czupryniak from the University of Rochester, who is a PhD student working with me and the rest of the group on some really exciting topics. And we're delighted to hear about his new work with colleagues about artificially intelligent Maxwell's demon for optimal control of open quantum systems. As I like to joke, this is the unholy union of artificial intelligence and Maxwell's demon, creating a Terminator-like robot that will kill us all. So with that note, why don't we have Robert kick us off here.
All right, let's go. So first I want to mention that this presentation is based on our recent preprint that was released just Thursday last week. I was presenting it in recent CQIQC in Toronto, Canada. As a poster, it had excellent reception. And the first thing I want to point out about this paper is like really not scientific thing, but it's kind of like the reception, like the way it was received by the community. Here's your joke, Andrew. Where in fact Andrew made that comment. Also Jens Eisert made a post on that one on LinkedIn, and it was like one of the most engaging posts from his profile over there. Like the paper itself had fantastic reception. I was talking to a lot of people in Toronto about this paper, and there's an obvious question that I want to explain is why is that the case? So the objectives I want to achieve for this paper is, first of all, to position it in the field in the sense why it might be interesting, why it might be worth for people to know about it. Second, I want to show you the technique we are using. I want to show you our results and to extract some sort of less from our results. So why is that the case that like not only physicists, but also other other fields might be interested within the paper itself? Like as Andrew called it, it's a marriage of fields, possibly unholy, in the sense that, first of all, we have physics in the sense that we study the quantum Maxwell's demon setup, and also we work within the context of control of open quantum systems. We have also the field of artificial intelligence, in particular the technique of reinforcement learning, a technique that, as I found out, it's not something that is being frequently used, and I will explain that technique in a little bit more detail later. And finally, I'm not sure if that comment is appropriate because I have no expertise to talk about it, but possibly we have some point within the context of philosophy. Why is that the case? The reason is that if you have artificial intelligence models, neural networks themselves, then it is usually the input and the output of neural networks that have certain interpretation, but the neural network itself is kind of a machinery that you use in order to produce the results, but that machinery doesn't have any specific interpretation. In our case, in case of our paper, it does. Let me start from the beginning. Let me try to position the paper within kind of grand scheme of things. This positioning might be incorrect, but I will do it anyway. So everything started probably in 1867, long time ago, from the letter from Maxwell to Tate. It's kind of a screenshot from the paper from the cited website, where Maxwell postulated for the first time the problem of Maxwell's demon, of the classical Maxwell's demon. It is the problem that is being referred to right now within the standard courses on statistical mechanics, for example. This problem is not only interesting from the science perspective, but also from the perspective of general population, in the sense as we can find a lot of articles about it, we can find a lot of artwork about it, where the demon, this weird creature, is portrayed in kind of artistic way very often. And Encyclopedia Britannica defines Maxwell's demon as a hypothetical intelligent being or functionally equivalent device capable of detecting and reacting to the motion of individual particles. So within that little sentence, the definition goes on, but we have the notion, first of all, of some form of intelligence, but also we have some notion of something that I will call feedback control over here. And how does this little device works? Like, and first of all, why was it interesting? Because seemingly at the time it seemed to violate the laws of physics. Here's a little screenshot from Berkeley. The initial idea is that you have a box with gas, you have a division between two parts of the box, you have particles starting at equal temperature. The demon has, first of all, the power to close a little hole or open the hole between two parts of the box. And moreover, the reason why it is called the demon is that it has this superhuman ability of tracking all the particles within the box itself. The procedure it produces is that, first of all, as one of the particles is about to go through the hole, and it measures the velocity of that particle, it gains some sort of information about it, and based on that information, it performs the feedback. Like, originally, it was proposed that if you allow only slow particles to go from one side to the other and fast particles to go into the opposite way, then you can seemingly violate the second law of thermodynamics. That issue was later resolved by connecting the theory of information with thermodynamics. But here we look at this setup kind of from another point of view. In the sense you can perceive it not as a demonstration of violation of the laws of physics, or apparent violation of the laws of physics, but you can look at it as a demonstration of a thermal machine where our objective is to pull one of the pieces of the box. This is in fact what will be our objective later. In the grand scheme of things, like there were different variations of such Maxwell's demon that were kind of studied. And I'll understand Maxwell's demon as a device where we try to cool something and we have some notion of feedback control. So we have this classical Maxwell's demon, the era of which possibly started in this 1867. Later, we had the emergence of quantum thermal machines. The paper I'm citing is not specifically related to quantum Maxwell's demon. It's a slightly different system. In any case, like it's the earliest one I found about quantum thermal machines. Later, within Andrew's group, there was a lot of work done on quantum thermal machines within the context specifically of quantum Maxwell's demon. And so we have the emergence of quantum tools, quantum techniques that were used to study such devices. And possibly right now, like we have the emergence of AI techniques that will be used to study such devices. That will be rather unusual. It might be considered a bit unclear whether we should cite our preprint right now or one of the earlier papers, but this preprint is the one that makes an explicit connection between Maxwell's demon and artificial intelligence. And the other paper I have in mind, Paulo is the author anyway. Paulo is also the main author of the paper, so I don't think he minds. In any case, let me give you an example of quantum thermal machines. So this is actually citations from Kahn's paper, and almost all of the authors were involved, like within Andrew's group, Srinath, Kahn, Bidek, and obviously Andrew, where we have one qubit attached to a reservoir. So just like before, like when you had this one box, within the box itself, you had the division, and like these pieces of that box, you can consider these two pieces as two separate boxes with a thermal contact between them. And now what we do is that you can imagine that you replace one of these boxes with a qubit itself. So now you don't have two boxes together attached with a thermal contact between them, but you have a qubit attached to a reservoir, also with a thermal contact between them that can be switched on and off. And the cycle that Kahn has studied in a slightly different context, but it was still a studied cycle, is that first of all, you begin in thermal state, marked by this little star, then you measure. For purposes of this example, the measurement is projective. You measure it in the z-axis. As a result of this measurement, you end up being either to the left or to the right of the Bloch sphere. Then, based on the result of the measurement, you perform either clockwise or counterclockwise rotation. You end up being at the bottom of the Bloch sphere, and then you thermalize the cycle, coming back to the original state of the qubit itself. You go on, and that procedure achieves cooling because during the thermalization stroke, the energy is being extracted from the bath. You can look at this cycle also from a slightly different way. Like In the sense, like you can look at this, you can look at it as actions performed in time. So what you can think about is that suppose that you have the time axis right now, and you divide this time axis into separate discrete bins. Within each of these bins, you figure out what kind of action do you want to perform, and you try to arrange these actions in a way that the cooling power becomes optimal in that specific case. So the cycle that was studied within Kahn's paper would be kind of these repeated sequences of orange, blue, green, orange, blue, green, and it goes on. But also, like, you can ask, like, if you want to figure out whether or not this given procedure is optimal, then you may want to study possible other sequences of actions. Maybe they would offer some advantage. So examples of such sequences may include, for example, something like this: constant orange dots corresponding to constant thermalization. This policy doesn't really make sense because in the end, it's like not extract anything. After a while, you just bring the qubit into thermal state and that's it. But it needs to be studied, and you need to figure out that this policy doesn't make sense. You need to make a conscious effort about it. You can figure out possible other policies where at the bottom you have these actions arranged in a slightly different kind of randomized way. That one would offer you some advantage. In fact, within the context of Kahn's paper, projective measurement, the cycle on top turns out to be optimal. But once you introduce complications, then it's like it gets more complicated. In particular, the complexity arises is that due to the fact that, for example, if you have 1,000 of these time bins and within each of them you have a choice of performing 3 different actions, then you have 3 to the power 1,000 of such sequences that you possibly might want to study. Obviously, that's a lot. And such problem is often impossible to solve within conventional techniques. And it should be noted that once you introduce variations to the setup, in the sense the action space within Kahn's paper is just X measurement, feedback, and thermalization. Once you start introducing complications within such setup, the problem becomes even more complicated. So for example, you can consider some tunable controls on your qubits. For example, you can vary the gap. You can introduce the weak coupling between the qubit and the buffer itself. So really to observe the effect of thermalization, you need to wait for multiple time steps. You can consider weak measurements. So in order to see any sort of effect due to the measurement of the quantum system, you may want to repeat it multiple times. You can complicate the measurement and allow the adaptive measurement basis, so not necessarily sigma X measurement by something, but something else. Or you can consider other setups, for example, at 1 qubit, at 2 qubits, at more qubits, etc., and see what happens. In any case, like we have these many complications of that problem on top of this number, which just makes the space, like the action space, like, I'm not sure if this is really the proper term, like it makes the number of policies kind of, we call such like such procedures that put above, I will call them policies within the context of this presentation. The number of policies that we would need to explore in order to find out what's the right one might be just too much for us to figure it out. And sometimes it's possible to guess the right one, but sometimes it's not. And within our paper, we use rather unusual technique in order to figure it out. In the sense that we'll have certain quantum system attached to a heat bath, and we'll be allowed to perform some sort of action on that setup of quantum system in the bath. For example, within our case, it made sense, like thermodynamically, to either apply measurement or to allow thermalization, or to evolve the system according to some unitary evolution, according to some Hamiltonian. As a result of that preparation, some sort of information will be passed from our system to our daemon. For example, the measurement outcome may be passed over there. Like our daemon will gain that information, and then based on that information, it will make the decision with what kind of action to perform. So it should be noted, like the reason why I introduced this unusual interpretation of the neural network itself is that in fact, our neural network is the one that will make the decision. Therefore, we make like sort of this far-reach statement that possibly the neural network can be interpreted by like Maxwell's demon-like creature. It should be noted that this framework is rather general, in the sense that our objective is to put a buff, but we can choose the quantum system on which we operate on, and also we can choose the action space. Therefore, we are able to study different variations of quantum Maxwell's demon. And that's what we do. In fact, within the main body of the paper, as I checked it out, we trained about 100 different neural networks just for the main body, each of them corresponding to a slightly different variation of quantum Maxwell's demon. So like, quite a bit of results to study in that sense. That allows us to also start, like we narrowed down the specific quantum system to either be a qubit, most of the setups, or 2 qubits, like it's just one section, but it's an important section. And we have studied within the paper itself different kind of timescales that might appear within different realizations of quantum Maxwell's demon. In the sense that, one of the sections we studied the thermalization-dominated timescale, in particular the coupling between the quantum system and the heat bath was weak, so we needed to repeat the thermalization stroke many times in order to observe any significant effect. There was also measurement-dominated regime, where we modeled it by making the thermalization almost instant and the unitary fast, but the measurement was being weak. We also combined these two effects within like kind of this part. And in one of the sections, we made all timescales relevant, and it was related to the 2-qubit setups that we have demonstrated over there. In many cases, like within this presentation later, I will present you like some subset of the results that we have that I found very interesting. But it's kind of my personal choice in that sense. Let me talk a little bit more about the reinforcement learning framework itself. So what we are doing is that we are dealing with a technique where the neural network, by repeated interaction with its environment, tries to learn an optimal policy in order to realize some specific task. Like within the, it should be noted in here that we are dealing kind of with two different fields, in the sense artificial intelligence and physics, and within both, like the environment might mean slightly different things. So for example, in physics, like when we have the qubit attached to a bath, and this bath is often referred to as the environment, while for the neural networks, the environment it's basically anything outside the neural network, so it can be quantum system itself. So the notion of environment is slightly different between those two fields. I hope that I will manage to make this presentation in a way where whenever I say environment, it will be rather clear what I mean. In any case, the neural network makes a decision to take some specific action from a set of discrete actions, which we specify to be either this thermalized measurement or unitary evolution. Or there might be some continuous controls that we have on our system, like the mentioned qubit buff or choice of measurement basis. This action is being performed on the quantum system. As a result, the state of that system gets updated and some information about it gets passed to the neural network. It also introduced the notion of the reward itself, in the sense that we'll have certain objectives that we'll try to optimize. In our case, since we want to cool the buff, the reward is just the cooling power. But possibly there might be some sort of notion of penalty that I'll introduce later. As the neural network receives the reward, it tries to, it gets the reward and it uses that information to update its policy. So that symbol pi, and here is the policy. You can interpret it as probability of choosing some action given the state of knowledge of the neural network. So the information about the quantum state that gets passed into the neural network. It's done in a way that optimizes the long-term expected sum of rewards. So if we optimize over just cooling power, we optimize over the long-term expected cooling power. So for example, it will be optimizing not only 3, 4, 5, but for example, 1,000, 1,000 time steps, something that is perceived as long. Let me make a brief aside from our technique to kind of possibly make some sort of analogy with other popular fields. Where game of chess, in fact, within the context of reinforcement learning or in general computation methods like turned out to be extremely interesting because it provided us with some excellent demonstrations of what computers are capable of doing. And like the first of such demonstrations, massive demonstrations, was given in 1997 with the match of Garry Kasparov versus IBM's Deep Blue. In 1996, Kasparov has won such match of human versus computer, but in 1997, Kasparov was beaten, and ever since then, computers completely outperformed humans when it comes to the game of chess. Another significant development in the field of chess engines, like by chess engine, we refer to it as some sort of like computational thing that can play chess well. Another like computational development, significant computational development came with the paper of David Silver and collaborators within the Google's DeepMind group, where they used reinforcement learning to master like different board games, where they included chess, shogi, and go. Since I have no idea about shogi and go, I'll do just chess in this presentation. In any case, we have this notion again of repeated interaction of the neural network itself with the environment which we can perceive as the chessboard, and by playing the game of chess multiple times with itself, the neural network learned how to play that game well. So if we try to make the analogy right now for AlphaZero itself, the rules of the game were given by the rules of the game of chess, while for our reinforcement learning Maxwell's demon, the rules of the game are given by the laws of physics and the constraints of the system that we try to consider. The board that we use for AlphaZero is just a chessboard, while for the Maxwell's demon, this is like not strictly correct because the board itself is kind of the knowledge that we pass to the demon itself. So it can be the knowledge about the quantum state of the qubit, which can be represented as the point of the block sphere, but also it can be some other pieces of information that we might pass to the network itself. The actions that the neural network takes within the games of chess are the moves that we have over here. So, look, if you recognize this game, we played this game a year ago. So, AlphaZero agreed. Actually, it was LiDAR-Zero. Agreed with that particular move. In any case, the move that the neural network makes is the move over here. The reason why I mentioned the name LiDAR-Zero is that Google's paper, like this AlphaZero, was later reproduced by like another set of people, and it's resulted in another engine called LiDAR-Zero. In our case, an operation like a move on the chessboard corresponds to an operation we perform with quantum states. So, for example, the neural network might decide thermalize. So that will be a move. Like we take the pawn from the bottom of the block sphere and we move it kind of to the center. And the objective of the game for the neural network itself is to give the checkmate, while in our case, the objective is to figure out the procedure that results in optimal cooling of the buffer. So we have kind of different notions of the reward in that sense. Let me make that objective more specific because within our paper, like we have really two options. Like on this slide, one is really the subset of the other one, but I believe it's still fine. Where within some setups, we have just optimized over the long-term expected cooling power, noted here by the brackets and P. While in the other setups, we introduce some sort of notion of the penalty, the sense that you might decide that, for example, it's particularly difficult to perform some sort of specific action on our quantum system, and there might be some penalty term associated with it. Maybe there's like some thermodynamic cost associated with some specific operation. We might want to assign penalty to it. This penalty, in our case, in the spirit of the original Maxwell's demon device, we have picked the Landauer's principle that defines the penalty we apply on the act of measurement. And in the end, we optimize over this trade-off of power and this term called dissipation. where we introduce some trade-off coefficients C that defines how much like we prioritize over optimizing over just going to power, or how much do we care about the penalty itself. So now, after this like introduction of the technique and what we were doing, it's time to move into the setups themselves. Where the first of these setups was studied by Paolo Erdmann, another author of the paper. Within this setup, we decided to limit our action space to either perform a projective Z measurement on the qubit itself, or to perform a slow thermalization. So the coupling between the buff and the qubit was weak when we like switched on to thermalization. But also on top of that, we introduced a tunable control of the qubit gap itself. And that resulted in the end in a policy that is kind of depicted on the plots on the right-hand side. I think let's pick the plot D to explain the policy itself. So it's kind of hidden in the bottom right corner over here. This plot is the plot of the control of the qubit gap, U of t, over time. I would not pay specific attention to the units and try to understand this process more in like quantitative sense. So in that sense, like you can imagine that the qubit starts in the ground state, for example, like over here. When it starts in the ground state, you can switch on the coupling between the qubit and the reservoir. During that coupling, like when it's switched on, you have the thermalization being performed. At some point, like the daemon just decided, okay, I have extracted enough heat. I'm gonna power the qubit again by the measurement. Suppose that I again end up being the ground state. I repeat that stroke itself. At some point, we have these switches within the qubit gap between the positive and negative sign. It's kind of like a way that, like a funny way in which Paolo introduced the rotation of the qubit, because switching the sign of that gap corresponds to rotation of the qubit, kind of like this from top to bottom, something like that. And as a result, after that rotation, like if it ended up being the excited state, it finishes in the ground state, you thermalize again over here, and you until some point the procedure repeats. So the neural network itself figured out that like it should perform these thermalization strokes interchanged with the measurement. And moreover, the plot above corresponds to a very similar policy, something very similar that I have described before. However, the thing that we try to optimize here is the power dissipation trade-off, in the sense that Paolo included some sort of penalty on the measurement itself. And the reason why you have the measurement strokes kind of close together on plot C, and further apart on plot D, is that there was higher penalty on the measurement term that was associated with that specific plot. Moreover, like the neural network figured out some non-trivial control of the qubit bath, especially during the period it was being thermalized, that resulted in some sort of an advantage over policy that Paolo called interpretable, that was mainly done without this tunable gap. This advantage is like especially clear on plot B over here, where Paolo compared like the interpretable policy that happened without the tunable gap, and the reinforcement learning based policy, which are marked as dots on this specific plot. It should be noted that there are not as many dots over here, because at least on my computer training, one of these dots is about 40 minutes of training. Let me move on. So that's an example kind of a setup where the thermalization dominated kind of the thermalization timescale was the most relevant. The results are sort of make sense for us. They were very encouraging. And now we'll move on to the setup that was more examined closely by us within like our Chapman's group, which was the setup powered by dominated regime, in the sense that our contribution was that suppose that the measurement was not really a projected measurement, but you performed some kind of weaker forms of measurement. And the measurement in here is still remains sigma x measurement. We also have a fast thermalization. We'll have a unitary rotation about the y-axis that the daemon will be allowed to perform. And the unitary rotation will be performed with an angle that the reinforcement learning agent can pick. This set of actions, well, I think they exactly correspond to the set of actions considered within Kahn's paper cited before, with the exception that we allowed this for this tunable control of the unitary rotation angle. And this measurement operator is the one that we'll use in order to realize the sigma x measurement. The key piece of information about it is that the projected measurement would correspond to the case of kappa equals 1. Kappa equals 0.5 corresponds, I think this one just evaluates to an identity when we plug that thing in. And any cases in between 0.5 and 1 would correspond to some sort of in-between kind of weaker form of measurement. And these results were extremely encouraging for us because, first of all, the plot above exactly reproduced the policy from Kahn's paper, which was encouraging. Like, look, okay, you might say it didn't really produce new results, but the reason why it was interesting is that it reproduced some piece of human knowledge that we had from the past. In the sense that we have the policy that I have described you before. In fact, what I have shown you before is the exact screenshot from this reinforcement learning policy. And if we observe the actions taken by the network over time, we have these orange, blue, green, thermalized measure feedback, thermalized measure feedback sequences. So it was very encouraging for us. Also, it was very encouraging that the network itself decided to rotate the negative z-axis all the time, which kind of makes sense because in the subsequent steps, it allows the agent to extract most heat during the thermalization stroke. We can reduce the measurement strength. So the setup below is the same set of actions, but significantly lower measurement strength. So as a result, due to the result of that measurement, you will not gain that much information about the observable being measured, but also you will not, the measurement itself will not affect the quantum state itself that much. So you can imagine that we start in the thermal state, just like in the plot. As a result of the measurement, we can go either slightly to the right or slightly to the left. Maybe I can like show a bit with my fingers because my cursor a bit lags behind. Go either slightly to the left, right, or slightly to the right as a result of the measurement. Later, let's say you ended up on the blue dot that is slightly to the right. You repeat that measurement because it's a blue dot itself. And you keep going until the moment when you reach some target purity of the quantum state. When you reach the some target purity, it is marked here by the green dot, you rotate the qubit to the negative z-axis, and then you perform the thermalization and you go on again. The interesting thing about this procedure is that it introduced a novel effect for us that I don't think was known before, in the sense that the neural network has shown that these sequences of measurements that are performed until reaching target purity correspond to performing random walks in state space until the target purity is reached, like for example over here, and then we rotate, perform the feedback, and thermalize the qubit. So that was like very encouraging result because first of all, it looks nice, and second, like it introduced like some sort of novel policy that was not known prior to the AI techniques. Let me switch to another set. This will be exactly the same thing as before. However, this time I will fix the unitary rotation angle to be rotation to the negative z-axis, because we have seen that for previous cases, it was always the case that the network rotates to the negative axis. I can do it just as well here. It makes the training of the networks converge faster. It is kind of helpful and it makes sense. However, I introduced a complication in the sense of adaptive measurement. So during training itself, the network can say that you either perform the rotation or you thermalize. And when you perform the measurement and by the color on the dot on these plots, like we mark the measurement type over there. So for example, a red dot would correspond to sigma x measurement, while a blue dot would correspond to sigma z measurement. And Again, interesting things happen as we started to reduce the measurement strength over here. The sense all measurements are performed with fixed strength, we can just tune T on. Network is just allowed to tune T on. For the projective measurements, once the network was allowed to perform these almost projective measurements, then we start with the Z measurement. We go either up or down on the block sphere. If we go up, the network elected for the unitary rotation to the bottom of the block sphere, and then it thermalizes and repeats the process over again. Once we reduce the measurement strength, we observe sort of the transition between policies, in the sense that we start again with a Z measurement. Then as a result of the Z measurement, we go either up or down. However, here we have the batch of X measurements. As a result of such X measurement, you go either to the left or to the right, you rotate, and then you thermalize, you repeat the process over again. So kind of we can mark the possible trajectories allowed for the neural network by this kind of set of arrows, like in here, corresponding to like way more complicated policies. But the interesting thing we observed as we were studying this problem is that we have seen these abrupt transitions between policies as we reduce the allowed measurement strength for the DIM. So you might at this moment ask the question, kind of as a sanity check, okay, so we have kind of increased the demon's power by allowing for this adaptive measurement basis. And does it provide any advantage in terms of cooling power? The sense like, does the reward that the demon obtained as a result of such measurement, is the power of allowing adaptive measurements significant enough to like produce advantage over the other policies? And in fact, in the end, it is. So what we have done is that we have trained several neural networks, but for some of them, we have allowed for adaptive measurements, and for some of them, we fixed the measurements to be either like sigma X or sigma Z. In all cases, we observed the advantages of the policy with adaptive measurements, which makes kind of logical sense. You can like kind of observe these blue dots over here, like on the bottom right of the block sphere, where the ratio of the cooling powers when compared to the sigma Z measurement power policy and adaptive measurement power policy is almost the same. And the reason why these two plots are almost at the value of 1 is that both neural networks in that case converge to almost the same policy, where different variations were probably the results of imperfections within the, of small imperfections within the reinforcement learning training. Let me now move on, basically to the same setup, but this time I allow the penalty to play the role, in the sense that for the sigma X powered measurement and adaptive measurement that I have shown on the previous two slides, I have optimized just over cooling power, but this time I allow for the measurement penalty, so I optimized over this trade-off power and dissipation that I described before. The measurement is kind of being progressively more penalized across the policies. And you can observe that as we increase the measurement penalty, we again observe these abrupt changes in policy. Kind of in a similar way when we reduce the measurement strength, and we also observe abrupt changes in policy. Here it's the penalty that plays the role. So we fix the measurement strength to be kappa 0.9. This is where we started. It corresponds effectively to this plot over here. It's the same network that produced. Is it the same network? No, it's a slightly different network that actually produced this plot. And then we reduce the measurement strength to 0.9. We observe abrupt transition into a policy that corresponds to cooling power by sigma Z measurement. It remains until the moment when we studied 0.5 as the trade-off coefficient, but then as we increase the measurement penalty, reduce the trade-off coefficients to 0.6, we observe another abrupt transition between the policies, which is the sigma X powered cooling, same as the one studied in Kahn's paper. As a result, later, we have trained several neural networks corresponding to different values of the trade-off coefficients, and then we have plotted the power versus dissipation, power versus efficiency over here. On both plots, you can observe that the points corresponding to different trained neural networks arrange themselves in 3 batches over there. The reason why you have these kind of 3 discrete batches, and the reason here is that for these points, we have these abrupt transitions between different types of policies. So for this one, this policy corresponds to these 2 points. These 2 points correspond to the value of trade-off coefficients of 1 and 5. Then we reduce. We observe abrupt transition to the set of blue points over here, and then we reduce again the measurement penalty. There is abrupt transition to the set of red points. There are actually 2 red points over there, 2, possibly even more. I'm not exactly sure. Finally, so it produced for us like many interesting results in many different contexts. Like showing you like several variations of quantum Maxwell's demon. But all of these setups were pertaining to the setup of 1 qubit. So there was a question, okay, can we generalize it and study multi-qubit setups with that? And it turned out, why not? In the sense, we just modify our quantum system, we modify our like set of actions that we are allowed to perform, but in general, like the training method itself remains the same, the core of the algorithm remains the same. And we studied a 2-qubit setup where this time the set of action was either slow thermalization of qubit number 1, it's the left qubit defined as the main qubit, or we can perform projective measurement in the z-axis of qubit number 2. So here you can observe that we can thermalize through 1, but we power the setup through qubit number 2. And we can also allow the unitary evolution between the qubits, where for this slide, I have picked the example where we pick the interaction Hamiltonian like this, in the sense that if one of the qubits loses excitation, then the other must gain, and the other way around. Yep.
So basically, in this setup, you have all the timescales.
Yeah, exactly. So we have done it to kind of make all the timescales kind of comparable. Like, so we have first of all slow thermalization, like even though the measurement is being projective, then the effect of the measurement, like the measurement itself must power the whole setup, not just the 2 qubits. So the information due to this measurement, or the kind of the way the measurement itself affected the setup was like needs to be transferred kind of from the second qubit to the first qubit. I'm not sure if I explained it right. And it is being done with the unitary evolution through this Hamiltonian over here. So what you can imagine over here is that, like, for example, you can imagine that this main qubit starts in a thermal state. Suppose that you measure the second qubit, you keep the interactions off for a second. You measure the second qubit, and this qubit is measured in the ground state. However, you would prefer to have them the other way around, in the sense you would prefer to have the main qubit in the ground state, the other qubit can be in whatever effective. That's exactly what our neural network has figured out to do. So in particular, when we study like these plots of concurrence, they look particularly nice over time, then this kind of emergence of concurrence over here and like decreases corresponds to establishing entanglement between the qubits. Like this entanglement is established kind of via the unitary interaction with this Hamiltonian, and it goes on until the moment when you perform some sort of a swap operation. When the swap is finished, then you decide to thermalize. It corresponds to the sequences of orange dots. It corresponds to this thermalization of the main qubit and measurement of the second qubit. So again, if it ends up being the ground state and this in the thermal state, you flip them around and you go on. You might also have some situations where the other qubits ends up being in the excited state, but we kind of covered that situation in a bit weird way by allowing the control of the qubit gap itself. And you can kind of flip the excited state to the ground state by flipping the sign of the gap from plus to minus. And that's indeed what the network does, in the sense that, especially if you consider the plot of the gap control, same U of t as here, over time itself, then you can see that sometimes this gap controls flips from positive to the negative values for the reasons I have mentioned before. During the thermalization stroke, the qubit is being measured. It doesn't matter really when it's being measured during that stroke. That's why this blue dot that sometimes can be visible over here. Sometimes it's kind of at random points during the thermalization stroke, and the process kind of goes on. The interesting thing is that it was mainly Paulo that studied this particular policy, and he was able to postulate something that makes sense, in the sense this swap, measurement, and feedback kind of cycle. But what he was not able to guess is that there's one more feature within this policy that provides significant advantage to the reinforcement learning algorithm over this interpretable algorithm. And this feature is this ramping of the qubit gap that we have kind of seen before as well. In the sense that during the thermalization stroke, there is some sort of non-trivial ramping of the qubit gap. And when we compare the policies with and without ramping that are marked with red dots, like reinforcement learning, and red interpretable, this interpretable is without ramping of the gap, then we observe that reinforcement learning indeed provided us with significant advantage in cooling power over the other policy. And with that set of results, I'm almost finished. I just want to leave you with some key messages within our paper. So first of all, we have this very unusual interpretation of our neural network, which is not only used to produce the results, but literally the neural network itself can be understood as the quantum Maxwell's demon that makes the decision on what to do next. Second, the reinforcement learning framework is used in finding these optimal feedback control strategies in our open quantum systems, which turns out to be a rather unusual technique. We might be actually one of the few groups in the world that might be using reinforcement learning within the context of quantum control. We found several control strategies that were almost impossible to find with conventional techniques due to the number of policies that you need to study and either accept or not accept. And finally, we have done it in several operational regimes, in the sense that we have studied several realizations of quantum Maxwell's demon. As I mentioned, it's about 100 neural networks corresponding to different realizations of that quantum Maxwell's demon that were used to produce the main results of our archive preprint right now, hopefully soon a paper. And with that, I want to thank you for your attention. I welcome questions. I hope you enjoyed it.
Very nice, Robert. Very nice. Questions?
Hi, yeah, thank you. This is pretty interesting. So, I mean, from a philosophical point of view, when people discuss Maxwell's demon, they're often interested in what is the thermodynamical cost of operating the demon? So I wonder if you have thoughts on what does it cost thermodynamically to use an AI type approach to have the demon make its decisions? Is that efficient thermodynamically, or?
The efficiency, in fact, can be quantified over here in the sense that, so within the quantum setup, you can understand that the measurement device powers in some way the device itself, and you can you can consider the amount of, not sure if that's a proper thing to use, but let's say power that was provided by the measurement device was translated into the amount of heat that was extracted from the reservoir. We do it, in fact, at different points of the paper where we compared the power itself that we extracted, the dissipation of the device itself, where the dissipation is that specific thermodynamic cost.
I guess I'm also interested though in the cost of operating the AI as well and making
operating the AI as well. I would guess at this point, this question might be very comparable actually to the questions that respectively, I think, Shillard, Landauer, and Bennett try to answer to such device. And I think that it's fair to even phrase it within the context over here, in the sense that there will be certain thermodynamic cost of acquiring, and in particular, the erasure of the information
Right.
that the daemon acquires, that it was possible to quantify. In the end, the planet connected the dots itself. But I don't see why this code would be different for the AI itself when compared to any other kind of computational device. So I don't see why it's different, for example, for TAS. I think the answer might be fairly comparable actually for the original Maxwell's daemon and for the AI-powered device.
There is sort of an extra thermodynamic cost in training the AI?
In training, I'm not sure. It's kind of a deeper question, because it's the question about actually performing the computation itself, which I'm not expert in. But if we ask for the boundaries just on operating it, not training, then I think the fundamental limit is given by this Landauer's principle.
Yes, sure.
I mean, if you have a training network, you consider the cost per run of the procedure, then eventually that training bit is just going to be constant. And so asymptotically matter.
The daemon himself is trained, right? He's trained to move it up or down.
Yeah.
So what we have right now, I think, is we want to say what is the most efficient way of moving it up and down.
Yeah.
So that's what I think we are arguing on.
Yeah.
But there is a thermodynamic cost figuring this out.
Yeah.
Assuming you don't use, assuming you do delete things, you do delete some information. But that's a constant. That's a constant cost.
Yeah.
So when you're considering the efficiency of the actual daemon itself, you have to look at per run.
Yeah.
And that's going to
eventually,
not enough runs that will eventually go. So.
But that's kind of also an interesting distinction, I believe, between like distinguishing between the procedure that is used just for training and the procedure that is in the end optimal, just to realize the policy itself.
Right. Thank you.
I wanted to ask about these abrupt transitions that you had in this model. So to what extent does this have to do with the fact that you're considering these sorts of discrete set of
Actions?
a discrete set of actions?
Yes,
so you have more of a continuum of actions with that.
That's actually a very, very good point. Like, in fact, we believe that like the main reason why we observe this abrupt transition either on this slide or this slide is exactly the fact that we didn't introduce some sort of tunable control in our system. So maybe it's possible that if you were to allow, for example, to tune not only the measurement angle as in this case, but also the measurement strength, that these abrupt transitions would disappear. But it's only kind of a speculation on my end, like not a full claim, but it's highly likely that there might be some tunable control that you would introduce that would lift these abrupt transitions as well.
Robert, do you have those slides for the continuous measurement version where you kind of blur out these lines?
Unfortunately, no. I should have. I can like try to switch it off and actually pull up the paper itself, if you don't mind.
Yeah,
No?
I can do that because I think that also answers answers Matt's question.
Yes, that's very interesting thing to do. Me first. Just pull up the paper, like so. The interesting thing that Andrew mentions is that we didn't only consider like one type of measurement. I did it for the constraint of this presentation, like discrete measurement, but we also introduced continuous measurements within our setups. And the interesting thing that the continuous measurements provided is that for some policies, they have actually kind of smoothened the policy itself, which would suggest like transition from like abrupt, a change from abrupt policies into something smoother. So let me actually share it. Okay, let's see. Let me first present you within some context over here. So first of all, in here in this plot, you have the examples of policies that are powered by sigma x measurements. Let me zoom out a little bit. By sigma x measurements and sigma z measurements, where again you have these dots, like it's blue dots kind of over here, like sequences of dots. They become kind of more vertical as we allow only z measurements, because only like the z coordinates is the main one that gets activated. But remember the structure of these dots, kind of how they look. And imagine right now that you would take a pencil and you were to smear out kind of these dots. Let's see what happens right now. And indeed, this plot over here corresponds to like performing like either strong or weak measurements, but continuous ones. And you can see this transition, like this, like kind of smoothing out this policy, which was also very interesting to us, that we roughly obtained the same thing. Also, the measurement is being performed until the moment where you obtain the target purity. After that target purity, which corresponds to these green regions over here, you would rotate. You end up being on the orange region, you thermalize, and you repeat the process again. But it might be somehow related, I believe, to this like abrupt transitions and between the policies that might be less abrupt over here. Because, for example, like in the smoother case, like for example, the transition for continuous measurements between strong and weak measurements would correspond to this like continuous pushing to the right or to the left of this green region. And but no abrupt transition over here is being performed, in the sense that you would not observe like this abrupt emergence of more dots, for example, as you reduce the measurement strength as in here. So maybe it might be somewhat related, but I must admit, like we haven't like studied it within that context. It's a very interesting context, though.
Yeah, and then also it also is like, so having discrete steps is much easier because you have either thermalization, measurement, or feedback, right? But having continuous axes, like talks between these three domains, it's going to make your problem more complicated.
And
So
so
they have
the
like,
space gets
exactly,
crazily
it gets crazy
Yeah,
expensive. So in our case, when you compare with the chessboard example, the chessboard just has discrete cases, but we have also one continuous case where it's like the gap of the qubit, which we can tune, or the angle of the measurement, which is continuous.
Try to load the slides again. In the meantime, do you possibly have any more questions?
Maybe, Robert, you could speculate a little bit on what next steps would be in terms of what new avenues of research does this open?
Oh yeah, of course. In that case, let me pull up actually the presentation again. If someone allows me to do it. Second. In that context, actually, it might be worth it to come back actually to our general technique, in the sense to reinforcement learning itself, where this framework, as I mentioned, it doesn't have to be used to the specific setups that we have studied within the paper. And what we want to do is to use this framework to study like more complicated setups, explore more physics. In particular, what we'll want to do is to like consider possibly like thermodynamic devices like thermal machines for multi-qubit setups, where possibly novel features might emerge that are not there for like just one qubit setups. Problematic thing that we expect is that with the increase of the system size and possibly with the increase of the amount of actions that will be allowed to perform on our system, well, we'll need more compute power effectively. The networks will become significantly more difficult to compute. But in any case, what we want to do now is to study like big quantum setups, not necessarily limited to just 1 to 2 qubits, but possible chains or lattices will be considered.
I have a quick question.
Yes.
So you introduce the tuning of the gap in the sense that you can invert the gap and the excited states become the ground state.
Yes, yes.
I was wondering, so I think that process needs to be very slow it needs to be adiabatic for the state to remain in the same eigenstate, right? Otherwise, it might become a
state to remain the same eigenstate.
Yeah.
But this has to remain better, but so it should be noted over here that in our case, so I assume that like the fusion might be related to this transition between flipping the levels, kind of. it's more of a mathematical trick for us kind of to figure out this unitary rotation where like the agent may allow to actually rotate the qubit around the y-axis. So kind of within this switch in the sign of the graph, we kind of silently introduce this, this kind of unitary rotation, because in the end, within the final policies, as you observe, the energy levels kind of never cross. But regarding the evolution of the system, yeah, I agree with you in the sense if the system is about to remain kind of roughly.
So are you like making a time-dependent Hamiltonian to achieve that, or?
Yes, it's time. In fact,
Right.
Paul has solved that equations, and like he has used it within our setups. He was the main person actually to do it. But yeah, it's that main time-dependent Hamiltonian that's being studied over here with time dependence being introduced by the control of the qubit itself.
Okay, let's thank Robert again. Very nice.